I'm disappointed that Dr. Farkas isn't here, but we'll do our best without him. Obviously, I never had the privilege of working with Dr. Farkas, and in fact, I've never even met him. And I was going to say I never met him till today, but I haven't met him today either. But nonetheless, he's influenced my scientific research for a long, long time. And in the opening few minutes of the talk, I want to tell you how that happened, and then go on and talk more generally about the whole field of ortho-para-hydrogen separation and separation of hydrogen isotopes. The whole thing's happened to me so long ago that I can honestly say it might be appropriate for a talk in the division of the history of chemistry, although that's a sobering thought. I was first introduced to the idea that two isomeric forms of hydrogen exist when I was a junior undergraduate at Holy Cross College. And my course in physical chemistry at that time was taught by my father. And we talked about ortho-para-hydrogen as part of the course, and that intrigued me very much. And my father introduced me to this book. And title page is there. It's a book written in published in 1935 by Farkas. And it's a very, very interesting book. Gas chromatography was a brand new technique at the same time, which again proves how long ago that was. And that idea also intrigued me, and so for a small thesis project which was required at my college, I tried to put the two ideas of ortho-para-hydrogen and gas chromatography together and attempted to make a gas chromatographic separation. And this is the title page of the thesis, which I dug up. And as you can see, that was some 32 years ago. And it's of modest historical interest, I think, to see what kind of equipment could be assembled together at what was then, and is now, for that matter, a really top-drawer liberal arts college, very well-equipped place. And I have a slide reproduced from an old photograph that shows the experimental equipment that I was able to assemble. I suppose it would be good to at least turn the light off over the slide. It looks a little antiquated by modern standards, and in fact it might have been antiquated by standards of the time at a big research university, but this was not a big research university. This was a small liberal arts college, albeit a good one. The essentials of the point of the thing is there was a 7-foot column of activated charcoal on which the separation was going to be tried. And you can see that was thermostated at room temperature. Now, I knew then that it would have been advantageous to operate at low temperature, but liquid nitrogen wasn't available in Worcester, Massachusetts in 1957, or not without great difficulty at any rate. And to get dry ice, to make dry ice acetone slushes, we would have had to travel across town every day to the ice cream factory, and that seemed like more trouble than we were going to put up with. So we tried the experiment at room temperature. The detector was similar to the one you use now. It's an old Galmac differential thermal conductivity cell. But it's amazing that at this college, which now has all kinds of computers and spectrometers and fancy equipment costing in the $50,000, $100,000 range, gratis of NSF in large part, at that time there wasn't even a recording potentiometer. So we couldn't take the output from the thermal conductivity cell and record it. What there was an old war surplus recording milliammeter. So we had to take the signal and amplify it, put it out in milliammeter, and that's what we did. So by modern standards, the equipment was rather simple, rather crude. Let me show you the results that we got. Here is a page from the thesis that shows a drawing. We didn't even have a Xerox machine, so I couldn't copy the chart. I guess no one else had a Xerox machine in 1957 either. This shows a separation, at least we thought it was a separation. I'm going to tell you in a few minutes that I think it's an artifact. But at the moment, at the time, we thought it was a separation. Helium as a carrier gas, and hydrogen, and the conditions for the experiment are given there. Rather slow flow, and this was reproducible. And we also made some runs with nitrogen as a carrier gas. And here are some recorder tracings, or tracings of recorder tracings, using nitrogen as a carrier gas. And you see quite an asymmetric peak, which would tend to indicate at least partial separation of the spin isomers. But down here at faster flow rates, very strange inversion of sign as one goes into the hydrogen band. Now, we concluded on the basis of this evidence and some other evidence that I haven't bored you with, that we had observed a qualitative separation of the hydrogen spin isomers of hydrogen, and we made that conclusion. In retrospect, I think that we were wrong. The separation factors, the ortho-para separation factors, fall off markedly as temperature increases, so that at room temperature, the separation factors were small. And moreover, there exist some anomalies in the thermal conductivity concentration diagrams for hydrogen, helium, and hydrogen, nitrogen mixtures. There's an actual minimum if you plot thermal conductivity as a function of concentration. Instead of a straight line, you get either a maximum or a minimum. And that could account for some of the problems as the concentration hydrogen-nitrogen or hydrogen-helium ratio changes as you go through the band. Nonetheless, we thought we had separation, and when I went off to graduate school, let me backtrack one moment. At the time, we didn't know that separation had really already been observed. In the early 1950s, a few years before this work, remember this work was in 1957, Sandler had observed enrichment on desorption of hydrogen from charcoal surfaces at temperatures around the boiling point of hydrogen. And much, much earlier, in 1941, in fact, Kramer in Austria had observed partial separation of the spin isomers of hydrogen, again by desorption from solid surfaces, charcoal again. So our conclusion was correct, that you could separate them, but I think our conclusion that we had separated them was questionable. Nonetheless, when I went off to graduate school at Johns Hopkins in 1957, I told my mentor about it, and he was the mentor of a number of other people in this room, Professor Paul Emmett. And Emmett was intrigued by the idea that we had perhaps separated the spin isomers of hydrogen, and encouraged me to continue this work, which I did. And we dropped the temperature to liquid nitrogen temperature, 77 Kelvin. Used helium carrier gas. Used a differential thermal conductivity cell to measure the hydrogen bands as the hydrogen eluted from the column, which was an alumina, a dehydrated alumina column, and we observed separation in short order. No problem. But just as we were writing up the paper, we got scooped, which was a thing of great chagrin to Emmett, and of even greater chagrin to me. This shows the paper that scooped us. It's by Moore and Ward, William Moore and Harold Ward of MIT, and it went in 1958 to the Journal of Physical Chemistry. And as you go down the diagram here, we have separations of ortho and para-hydrogen. The time is plotted this way. So para, which is the even 02468 spin isomer, is eluted before the ortho. And that's for a mixture of hydrogen equilibrated at room temperature. This is for a mixture of hydrogen equilibrated at lower temperatures in order to raise the para to ortho ratio, and various other conditions as you go on down. In fact, the authors even took samples, separated samples of ortho and para-hydrogen, and then rechromatographed them in order to show that this was not an artifact, and succeeded in making a partial separation of the spin isomers of deuterium. You'll notice that ortho-deuterium is eluted before para-deuterium, but remember that ortho-deuterium corresponds rotationally to para-hydrogen. Para-hydrogen occupies the 02468 spin states, whereas para-deuterium, where just the opposite is the case. For deuterium, it has to do with the naming convention. In short order, after that time, a number of other authors announced separation. Gant and Yang, and I'm sorry I don't remember where they were located, published in 1959. Van Hook and Emmett, published in 1960 from Johns Hopkins. Moore and Ward, published again in 1960, dealing this time with isotopic as well as spin isomer separation. Kwan and co-workers from Tokyo, published in 1961. Monkey and Safford from the Federal Republic of Germany in 62. Smith and co-workers from the University of Tennessee, published in 63. And all of these authors reported separation of isotopomers and isomers of hydrogen with various levels of sophistication and convenience. Most of the workers employed alumina columns, and most of them used a suggestion of Moore and Ward, in which they oxidized the hydrogen as it eluted from the column by passing it over a short tube filled with copper oxide at an appropriate temperature in order to oxidize the hydrogen to water. The reason for this being twofold. Most importantly, the thermal conductivity of water is much, much different than helium, whereas hydrogen is only a little different from helium. So this amplifies the signal. And secondly, the thermal conductivity concentration diagram for water in helium is much more nearly linear than that for hydrogen in helium. And so that takes care of the annoying plus and minus behavior that you saw in the tracings from my bachelor's thesis. So two problems were solved with this very neat solution. Let me show you another diagram, a few more diagrams. We'll start with this one. Since I'm the speaker, I get to show my work. And this is a page from the Van Hoek paper in 1960, which shows the separation of ortho and para hydrogen and hydrogen HD and D2. But you'll notice that HD, hydrogen deuteride, is not separated on this particular column from ortho hydrogen. The separation factor is just too small to elude it. Again, you'll notice the shape of the peak is a bit skewed, perhaps not quite as skewed as the Moore Ward separation, but still substantially skewed. And we suggested various ways to use this for the quantitative analysis of hydrogen mixtures. At about the same time, 1960, 61, 62, a number of authors recognized that the most useful reason to pursue this work would be as an analytical technique for mixtures of hydrogen, deuterium, HD, tritium, etc. And in that case, the ortho-para separation would do nothing more than complicate the issue, especially if ortho-hydrogen overlapped HD. And suggested that what one should do is poison back, selectively just a little bit, poison back the alumina with some paramagnetic centers, for example, iron oxide, because the paramagnetic centers catalyze the ortho-para transition so that the separation for ortho and para would be killed, while that for H2, HD, D2, etc. would not. And this, in fact, obtains, and these columns nicely resolve all of the isotopic isomers. And here are some examples. This is a 1967, taken from a 1967 paper by Conti and Lesample from Saclay. And some of them are poisoned and some of them are not, but you'll notice this particular column down here nicely separates ortho and para hydrogen, HD, HT, D2, not ortho and para, however, DT and T2. And here's another one. And here's a tracing with a column that's poisoned paramagnetically so as not to separate the spin isomers. So it's quite obvious that by cadiddling around with the column conditions, flow rates, temperatures, pre-treatment of the alumina, or molecular sieve, as the case may be, you can effect total separation. And there are just lots and lots of diagrams that I could have selected from the literature to illustrate that. The whole situation was reviewed by Akhtar and Smith from the University of Tennessee in about 1964. And since then, a lot of other separations have been reported, but I'm not going to review them. The order of elution is that you've seen, namely hydrogen, HD, HT, D2, DT, T2. Ortho-para separation factor is much larger for hydrogen than for deuterium, than for tritium. They fall off markedly with mass. The pretreatment of the surface is important. Here is a paper by Keith Hall and a co-worker, Ben Kuhlur. I confess I can't pronounce his name. I don't know the man. Hall looked at the ortho-para separation factor on alumina as a function of the treatment of the surface. And here we have a surface, the solid line, treated at 150 degrees to be dehydrated to make the active site. This says 140 degrees, but that's wrong. It's 240 or 340, or maybe it's 440, and I can't read it. At any rate, it's at a much higher temperature than the solid line. You see the separation is the elution times are changing a bit, the separation factors are changing, and as you treat the surface at the highest temperature, you lose the ortho-para separation completely. However, on that same surface, you find that the hydrogen, deuterium, tritium separation factors increase as the temperature increases. So the number of active sites, or the intensity of an active site, increases with the pretreatment temperature. And the speculation is that what is happening here is that as you boil off the water, the field intensity, this is an ion-induced dipole interaction, the field intensity at the surface increases, and that in turn gets to the point where it begins to catalyze the ortho-para conversion. So that the most active surfaces, most active for hydrogen, deuterium, tritium separation, are not active at all for ortho-para separation because they catalyze the ortho-para conversion. And this whole thing was worked out in a quantitative way in a very interesting paper by Kramer and Kramer. Now, it's interesting. Kramer, K-R-E-M-E-R, and Kramer, C-R-A-M-E-R. So that's not husband and wife, father and son, brother and sister, or brother and brother. It's two completely different people with two completely different names, at least as far as they're spelled. The situation that you see here is exactly what happens when you lose two NMR peaks as the rate of the reaction flipping to structures begins to be on the same order as the time constant for the NMR signal frequency. You lose the two peaks. They grow together. And so from the peak width, you can calculate that characteristic relaxation time. Here you can calculate the kinetics of the reaction from the shape of the peaks. Well, I've sorted through and that's a very interesting thing. I've sorted through the chromatographic data and put some numbers up here. These are mostly on alumina, and there's a number of references here, 7 different experimental references, and 1 theoretical calculation. And you can see a range of separation factors that vary from around 1.2 to 1.6 on ortho-para hydrogen, and the tritium varies accordingly. So there's quite a range of separation factors. The order of elution stays the same on whatever surface. You always find para first, ortho second, HD, HT, etc. But the separation factors themselves vary enormously according to the pretreatment of the surface. Now the problem, and this is a calculation that we're going to be talking about briefly. It's quite apparent, well, if you look at the theory of the separation, you can write the separation factor, which is just an equilibrium constant for surface adsorbed phase change. It's just a Henry's law constant. It's a ratio of gas phase and surface phase partition functions. And using the standard methods of beginning statistical thermodynamics, you can write Q as a product of rotational, translational, vibrational, nuclear, etc. parts. And if you assume that this separation obtains, you can then write down the partition functions for the different degrees of freedom. It's quite obvious that the ortho-para separation is connected with the rotational partition function because everything else is the same. It's got the same force constant, it's got the same mass, same strength, etc. And of course, the first principle of theoretical isotope effect calculations is that the potential energy surface for the two isotopic isomers is identical. This is, we think, true within the confines of the Born-Oppenheimer approximation, and deviations from the Born-Oppenheimer approximation are small. For molecules like hydrogen, they're real, but they're small, and so they're second or third order effects. So I've written out here the rotational partition function in the gas phase. For hydrogen, and remember J is even. For para-hydrogen, ortho-deuterium or ortho-tritium, it's odd for ortho-hydrogen, para-deuterium or para-tritium, and it's both even and odd for the asymmetric species, and this defines the moment of inertia and reduced mass. On the surface, the rotational, well, one looks at a situation like so. There's a few things you need to keep in mind. At 77 Kelvin for hydrogen, almost all of the population, rotational population, is in the ground state. In fact, 99.9% of para-hydrogen is in the zero rotational state and only a tenth of a percent in the second rotational state. And these are all tabulated for the different isomers and isotopes of hydrogen. The point being that almost all of the population is in the ground state for the orthopara species, and there are small amounts in the excited states, as you can see there. A reasonable model has been proposed by a number of authors, including Katorsky and White and other co-workers as well, King and Benson. You look at a hydrogen molecule interacting with the surface, it sits at some angle, so it can vibrate perpendicularly to the surface in the z direction, and when it tries to rotate, that rotation is hindered. And here's a typical kind of a potential energy function that's used to describe that. This is one suggested by Katorsky and White. It's rather complicated to work out the quantum mechanics of this. It's a lot of, well, it's 5 or 6 pages in the Journal of Chemical Physics filled with equations. On the other hand, if you assume that the rotation and the rotational and hindered vibrational degrees of freedom are separable, not coupled, as in this equation here, you can work it out very simply, and that's what King and Benson did. It's a more approximate calculation. This potential is basically a Morse function for the hindered vibration. A Morse function is almost a harmonic oscillator, and the well looks almost harmonic. And there's a separation of isotopic levels. King and Benson used a harmonic oscillator model, so their potential looks about the same. Actually, they cheated a little bit. What they did was they assumed that the interaction between the hydrogen and the surface was a charge-induced dipole interaction, which is a 1 over r4 attractive part to the potential, and some kind of a very steep repulsive barrier. Take it as a hard sphere barrier. This is a highly anharmonic well, and it pulls these levels together much closer than they otherwise would be were it harmonic. However, King and Benson cheated. They said, we'll use the charge-induced dipole potential to figure out what the energy of adsorption is. But in order to calculate the isotope effects, we can't solve the problem. They couldn't solve this problem, so we'll assume it's harmonic. So they basically took a harmonic potential well as far as the calculation of the isotope effects are concerned. So the King-Benson calculation and the Katorsky-White calculation are essentially identical. Both of them have a problem that they're too nearly harmonic. This is a more realistic potential well, but it's harder to calculate the isotope effects, and no one has done it yet. I had hoped that I would have that calculation complete by the time of this paper, but I don't. I'm working on it. This shows how the rotational energy levels are perturbed by the surface interaction. As you increase the surface potential hindering the rotation, the energy levels go up from, these are reduced, 0 for the 0, J equals 0, this is J plus 1 equal 2, etc., all the way on up. And you see there's a considerable energetic interaction here, and you'll notice that the rotational states, which are degenerate in the gas, 2J plus 1-fold degenerate, split on the surface, and of course this has a significant effect on the partition functions, and that has to be included in the calculations. And those numbers were so included. Here I have some quick results. I'm about out of time, all right? Okay, I'll be done in 5 minutes, maybe in 3. There's just some more algebra. You can all do algebra. The different contributions to the partition functions. The calculations that are extant in the literature ignore the fact that the internal vibration, which in hydrogen is around 4,000 wave numbers, has also got to be perturbed by the surface interaction, and that perturbation can be significant. Again, that's something that we're trying to take into account. But at any rate, here's the rotational contribution, which you can calculate this parameter from the ortho-para separation factor itself. Remember, we said the only difference there is the rotational contribution. So if we assume a model for rotational perturbation, which we've done, we have no reason to suspect that it's going to be the correct, in capital letters, the correct model, but at least it's a plausible model. So in using the ortho-para separation factor and that model, and taking the ortho-para separation factor to be 1.3, which is on the high side of the observed separations, you calculate a rotational hindering potential equivalent to 236 wave numbers. And here are the separation factors that you get purely from the rotational contribution to the partition function for all these different molecules. And you see they're rather large. You get up to deuterium, they're very large indeed. Now, it's interesting here, you see, the ortho-para separation factor of 1.4 drops off to a deuterium, ortho-para deuterium separation of 1.07. And by the time you get to deuterium, the thing is inversed. It's gone to 0.98. And you can see the reason for that lies in the fact that this slope of this m equals 0, L equal 1 state is less than the slope of the m equals 0, L equals 0 state. So when you come out here and you take these ratios and ratios of ratios, well, that's the numbers. That's the way the numbers come out. So we don't expect to get good separations for ortho-para deuterium or ortho-para tritium. The point is, by cadiddling the relative contribution of the rotational part of the partition function and the hindered translation, the vibration perpendicular to the surface of the whole molecule, you can come out with a set of parameters that pretty nearly fit the observed separation factors. And this is what was done by Kotorsky and White. And you see here are a set of calculated numbers according to the theory that I just outlined. And if you pick your experiment carefully enough, you can say you've got pretty good agreement. So it's quite clear that the theory does explain the gross features of the separation. However, I want to point out to you that at that level of theory, the Kotorsky-White or King-Benson level of theory, they have completely ignored any contribution from the internal vibration, which is also expected to shift when you take hydrogen gas and condense it to the liquid. The internal vibrational frequency shifts by around 15 wave numbers. And a 15 wave number shift amounts to on the order of a 10% separation factor. Remember, the temperature is low, and you don't have to change these partition functions, these energies, too much to make a big change in a partition function because the temperature is low. And this is at 77 Kelvin. A 15 wave number shift amounts to about a 10% isotope effect, and a minus 200 wave number shift amounts to a ratio of separation factors which is 0.6. The surfaces which are used, the surface voltages, the interaction fields, which are used in the Kotorsky-White or Benson-King formalism are very large. This is a very large electric field interacting with the hydrogen through the polarizability. And to ignore the contribution of the internal frequency is I think, rather short-sighted. Well, to summarize, let me tell you that we've concluded that the root cause of the physics leading to gas chromatographic separations of ortho-para-hydrogens and deuterium and tritium and the mass isotopes are well understood, at least in a qualitative way. The presently available models which describe the gas surface interaction predict the order of elution correctly and predict the magnitude of the separation factors correctly. But if you look very carefully at the agreement between theory and experiment, you find that numerical agreement is not exact. And it seems to us that the theory can be refined markedly by improving the description of the shape of the potential, by recognizing that it's much more anharmonic than has heretofore been recognized, and by including the contribution of the internal degree of freedom into the formalism. And as I told you before, I'm sorry that I couldn't report on calculations succeeding in doing that, but we're working on them, and maybe at the next meeting I can tell you that. Thank you very much.
There's time for one brief question, perhaps. There is one. Yes.
I just want to comment because during my PhD qualifying examination, I was asked all the questions that you were presenting today. Professor Emmett must have been working on this thing. And I had the ortho and parahydrogen pretty well worked out, and the deuterium sort, and then I got hit with the ortho-paratritium, and I couldn't do anything with that in this examination. So I am really interested in your work, and perhaps you could send me some reefers of it, so I can finally answer my qualifying examination questions.
There's a whole,
He must have had somebody trying to separate ortho-paratritium at the time, because he didn't know the answer either.
There's a whole and large literature on the separation of the isotopes and isomers of hydrogen on palladium and other kinds of metals, but especially palladium, because as you know, hydrogen dissolves in it markedly. And one suspects that there's a large classified literature on this too, because there's a lot of interest in separation of hydrogen, deuterium, and tritium in the bomb business. And so this is a very